Welcome back to the course entitled
Elementary Electrochemistry.
In the previous lecture, we have discussed about how one can relate the EMF of a cell with the gives free energy of that particular cell, and from that we tried to calculate the heat of reaction or heat of formation of a particular substance during the reaction taking place at the electrochemical cell. So today we are going to learn about the relationship between the EMF and equilibrium constant of a given reaction. So we will discuss how the electromotive force or EMF of a cell and the equilibrium constant of the reaction is related. This relation is called the Nernst equation. So, to start with, let us consider a chemical reaction taking place. In a galvanic cell. As PA plus QB is in equilibrium with RC plus SD. So A, B, C and D are the reactants and products, while where P, Q, R and S are the stoichiometric coefficient required to balance the chemical reaction. So then, from the reaction isotherm, the free energy change that is the delta G of this reaction can be written as delta G equal to minus RT ln Ka plus RT sum over nu ln A, where Ka is the equilibrium constant of the reaction and A denotes the activity of the reactants and products, right? Now when all the reactants and products are in their standard state, then their activities will be unity then the standard free energy change, which is written as delta G0, would be delta G0 equal to minus RT ln Ka, right? So then the equation for delta G can be written as delta G0 plus RT sum over nu ln A. Now in the previous class we have seen that delta G equal to minus NFE, then delta G0 would be equal to minus NFE0, where E equal to EMF of the cell and E0 is the EMF of the cell at standard state, right? So then if we replace these values for delta G and delta G0 in this equation, so one can write that minus NFE equal to minus NFE0 plus RT sum over nu ln A, or E equal to E0 minus RT by NF sum over nu ln A, and delta G0, which is equal to minus NFE0, is also equal to minus RT ln Ka, which we saw in the previous slide. Therefore, one can write E0 equal to RT by NF ln Ka, or simply E0. No, one can evaluate this, you can convert this ln to log and write it as 2.303 RT by NF log Ka, right? We have two equations that we have got here. So one equation is for the standard EMF, that is E0 of a cell in terms of the equilibrium constant, and the other one is EMF of the cell in terms of the activities of the reactants when they are not in their standard state. So in an approximate evaluation of Ka, one can use Kc in place of Ka, that is the equilibrium constant in terms of concentration, and activity terms can be replaced by the corresponding concentration terms, that is small c, right? So now if you try to evaluate this 2.303 RT by F at 298 Kelvin, this turns out to be 0.0591 volts. Okay, taking Faraday number as 96500, R at its standard unit, and temperature in Kelvin, one can evaluate the value of this constant as 0.0591 volts. So then one can write at 25 degrees centigrade, E0 of a cell is nothing but 0.0591 by N log Ka, and E equal to E0 minus 0.0591 by N sum over nu log A, and also one can write E equal to, we replace E0 by that expression 0.0591 by N log Ka minus 0.0591 by N sum over nu log A. All these are different forms of the Nernst equation. So then one can approximately write in terms of concentration E equal to 0.0591 by N log Kc minus 0.0591 by N sum over nu log C, right? So now if we assume, if we try to think about a Daniell cell, for a Daniell cell where the cell reaction is Zn plus Cu2 plus in equilibrium with Zn2 plus Cu, one can write Ka equal to activity of Cu into activity of Zn2 plus divided by activity of Zn into activity of Cu2 plus, which can be equated to activity of Zn2 plus by activity of Cu2 plus as the activity of pure metallic copper is equal to activity of pure metallic zinc, which is assumed to be equal to 1. So using this assumption that the activity of pure elements, pure substances is always 1, one can eliminate them and write this expression as Ka equal to activity of Zn2 plus divided by activity of copper 2 plus, right? So now if you try to calculate the corresponding E0 value for this cell, one can write E0 equal to RT by NF ln Ka equal to 0.0591 by 2, that is the charge of the cation log Ka, and we know the E0 for Daniell cell is 1.1 volt. So using that 1.1 volt as its standard EMF is equal to 0.0591 by 2 log Ka. So from this one can calculate the value of Ka equal to 1.7 into 10 to the power 37, which essentially means that activity of Zn2 plus by activity of copper 2 plus is nothing but 1.7 into 10 to the power 37, or one can write that activity of Zn2 plus is equal to 1.7 into 10 to the power 37 activity of Cu2 plus, right? So like this one can do some simple calculations based on the EMF, and one can calculate the equilibrium constant, and from that one can calculate the ratio of activities of the corresponding constituents. So based on this, I would like to give you one assignment or one problem for you to try. Calculate the equilibrium constant of the reaction H2 plus Cl2 in equilibrium with 2HCl if the EMF of the corresponding cell is 1.01 volt, and also write down the cell with appropriate reactants and the electrodes. Okay. So this is one of the problems that you should try to solve at home. This will help you in understanding the subject and basics properly. So now I would like to start discussing about different types of electrodes, because as you have already seen, there are types of electrodes where one gas is involved, like hydrogen gas. Somewhere you have a metal and metal ion electrode, and so on. So based on the type and nature of constituents, nature of chemicals used to form an electrode, there are several different types of electrodes. And these are called types of single electrodes. As you all know that a galvanic cell must have two electrodes, cathode and anode. Each of these electrodes are called the half cell or a single electrode. And depending on the type and nature of its constituents or the chemicals that are used, there are several types of such electrodes. So let us try to understand some of those one by one. The first one is a metal ion electrode. So here what you can easily understand that this electrode consists of a particular metal in equilibrium with its cation. So in this type of electrodes, a metal is used as an electrode in connection with its ions, that is cations. So when a metal rod is dipped in a solution of its cation, then the combination is called the metal ion electrode. Some examples are silver plus electrode, where the reaction is silver is in equilibrium with Ag plus 1 electron. Similarly, copper 2 plus, where the reaction is Cu metal is in equilibrium with Cu2 plus and 2 electrons. And there can be amalgam electrodes, where you have lead amalgam with Pb2 plus. So the reaction at the electrode is lead amalgam is in equilibrium with Pb2 plus 2 electrons. So these are examples of metal ion single electrodes. Each of these single electrodes will have their own standard electrode potential, and that standard electrode potential can be easily determined from the from the measurement using a potentiometer, using standard hydrogen electrode, or using standard calomel electrode. So like this, there are other single electrodes which we will discuss in the next class. Thank you.